Good morning. I'm Peter, and I'm here to talk about sane and safe C++ class types. And when I refer to sanity, I'm not referring to mental health issues. I know people have that, so please don't be offended if I talk about sanity. It's not about you, it's about C++ types. So, to figure out how to actually categorize types, I made a little map, and that's a typical quadrant thing. So you have things that are sane and other things that are safe to use. And if it's sane and safe, it's easy to use. That's the quadrant you want to be in. And there are other things that everything on the left part is things that require high discipline, maybe hard hats to go there. And sometimes it's really dangerous. And we have that thing called undefined behavior, and that's where you don't want to be at. And there are some things that are not that dangerous, but still ill-advised. So they might poison your code base because you have things that seem to be a nice idea, and everybody is using that in your code base, but it makes your code ugly. And I'm not sure if I can give you some examples of the poison, but you might have seen them at home or somewhere else in the code bases you have. First, I like to talk about values, because values actually belong in that green part. Usually values are really easy to use, they are safe, they get copied, you don't have to care about changing things unintentionally, because a value is just a value. And our friend Scott Myers says, okay, when in doubt, do as the ints do. Int might be the type that is gives the category of value types, but not always. Stay tuned. So value types in the standard, and in the concept of the standards, we have the concept of a regular type. And C++ containers assume that you put more or less regular types in as template arguments for the elements that you put in the container, and then everything works fine and smoothly. And if you put very interesting types in your containers, they might work partially or not at all, and you might end up in undefined behavior land. Stepanov originally actually said that that regular types includes ordering, so that standard less works, and that's important for the associative containers that sort the elements. In C++ 20, it's not only less than operator that defines the ordering, but the spaceship operator, so stay tuned for that. I still haven't used the compiler supporting it, or at least I haven't tried it, but that's the future to define sorting. So what goes into regular? You can compare elements for equality. You can default construct them. If you copy them, the equality should be given. So if you assign B from A, then A and B should be equal. They should be movable and move assignable, swappable, better without throwing exceptions, and all the things that you would expect from them. Now, if we fill out with categories of types that I would like to explain to you, we have things, value types, upper right corner, empty types. If you don't have data, you can't have races, so nothing can go wrong. And that's the corner where everything is sane and safe. But there are other types like OO polymorphic types, and then they are on the hard hat side of the quadrants. You have to make sure that you're not doing insane things with them. And there are other things like pointing types, which includes references, string view, span, which also require very high discipline. They can be quite sanely used, but only if you apply that high discipline and not doing insane things with them. And a category that's often not obvious is what I call managing types. Types that manage the lifetime of other objects. A canonical example is vector. Vector manages the lifetime and the memory occupation of its elements. And the vector, when the vector goes away, the elements disappear, but also you can retrieve a reference or a pointer or an iterator to a single element and work on that single element managed by the vector. And then there's the area of insane or ill-advised and dangerous things like plain pointers. In my opinion, plain pointers have no real use in user-level code in the standard library. In the user code in C++, sorry. In the standard library, we have a unique pointer that actually makes the memory management more sane, but still they might be null, so that's dangerous if you apply the dereference operator on them. But plain pointers, even though people say, okay, we should use plain pointers to denote single objects, the problem is they still allow all the dangerous operations on them, like indexing. And that's not what you want to do. And then I've seen code where you have very interesting combinations of special member functions. Don't do that. Rely on the rule of zero, or if you actually do something interesting, then you end up at least in the hard hat, high discipline area of polymorphic types or managing types, where you actually have to deal about destruction and so on. The only reason to write these weird combinations of special members is for testing templates. And I gave some examples yesterday. But the question is, where are the built-in types? They are not class types. Any idea? Would it be that quadrant? Sane but dangerous? Anyone there? Value types, sane and safe? Oh, you're so wrong. They are actually in that other area. I'll give you an example. Bool. Simple. There are regular types in char, bool, double, but. Just see what is the result of that, the answer assignment or initialization. What should go in there? It's a quiz. Who knows the answer? It's either yes or no. Is it easy to spot? Have you seen code like that? Made the same bugs? Any volunteers? Come on. It's a Boolean decision. Yes or no? So you say it's no? Okay, 41 modulo 3 is 2. 2 bit and 42 homework. Now, another interesting feature, doubles. Are doubles safe to use and sane? Someone has the opinion, no. What is the size of that piece of code, of that vector, of the set, sorry. You just have a vector of a couple of values, double values, class template argument deduction in C++17, and we insert division of each pair of elements in that vector. So the vector has 4 elements, so we have 4 by 4, 16 potential quotients in the vector, in the set. Minus the ones that you get when you divide by itself. What is the size here of that set? Is it? Divide by 0. If I divide 1 by 0, what do I get? Infinity. Not too bad. The problem is, what if I divide 0 by 0 in floating point? It's well defined. Not a number. I get not a number. What happens if I insert not a number into that set? Bad things, yes. Because not a number doesn't compare less with any other number, not even with itself. And the equivalence in a set is defined by not being less in both ways. So not a number is not less than itself and not less than any other number, and not any other number is not less than not a number, so any other number is equivalent with not a number. So that set has a size of exactly 1, because the first element you insert into it is not a number, and no other element can be inserted because they are all considered equivalent with not a number. Very interesting behavior, often forgotten when you put interesting types into associative containers. And the spaceship operator doesn't help with that because it's wrong. It has the same behavior with not a number. So actually, doubles are not strictly ordered. Another thing, that's a typical common mistake, and that's why people want to have span size returning an integer, which I consider a bad idea, and I'm open to other opinions. What happens in that case? Say it again. You get an infinite loop. Why? Well, size returns an unsigned integer. If you subtract -1, it still remains an unsigned integer. If that vector happens to have size 0, because it's empty, it will not work. And I becomes an unsigned integer. So for an unsigned integer, it's never less than 0, because that's how unsigned is defined. So we have a compiler will put that in true, and we have an endless loop regardless. Interesting behavior. So there are some problems with primitive types that put them into the hard hat, very dangerous quadrant. Integral promotion. Who can claim to know all the tricky rules of integral promotion by heart and follows them every line of code they write? I don't see any hands. Me neither, because it's really intricate. And sometimes you get interesting warnings by the compiler, and we learned yesterday, oh, you should better listen to your compiler. But very often what happens, oh, signed, unsigned mixtures in comparison or arithmetic, I know that it's okay, I just discard it with the cast so I don't get that warning. Sometimes we have the silent changes of values, like wrapping of unsigned or undefined behavior on signed overflow. And we know undefined behavior is not a place you want to be, because all your code is invalidated by that. Sometimes I would love to have the carry bit. And who doesn't know what a carry bit is, you're not old enough to appreciate the carry bit. Or haven't done assembly language enough. So we don't have that in C++, so the abstract machine doesn't allow us to detect overflow and signed numbers, or not even unsigned. We have the automatic numeric conversions. That's not integral promotion. So a bool can be interpreted as a floating point number easily, and vice versa, which is sometimes nice, but can be very surprising if you make mistakes with operator precedence. which is also a nasty thing with these many levels of rules of operator precedence. And the special values for floating point numbers that we already had talked about. Even the standard library implementations suffer from that. And there are other problems. What if I have a function with 3 ints as a parameter type? How do I know what the meaning of these 3 ints are? Is it fluximate 3 to 1 the right order to call it? Or is it the other way around, and which is which? And there are some approaches where people say, oh, we want named arguments on calling the functions. Not a good idea. I believe that's just curing a symptom and not solving it in the right way, because you still have 3 arguments, the primitive types there. And the good thing in C++ is we can actually wrap those primitive types in our own domain-specific types without overhead, except for some ancient compilers. The next thing is, if I mix signed and unsigned arithmetic, in the standard library we have size t and size types of containers, and they are for counting elements. Counting is based on natural numbers, including 0. So if I count things, I should stay in that domain. But if I add subtraction to the operator domain of natural numbers, I go into the domain of whole numbers. So if I subtract natural numbers, I might go out of their domain into the domain of integers. And we suffer from that in the standard library, that if we have 2 natural numbers represented as unsigned numbers, like size t, and if we subtract them, we still remain in the domain of unsigned and not signed. The reason is, well, they don't match because we have limited a number of bits for representation, but also it's very interesting things happen. For example, if you see that code, there's distance. Return type of distance is difference type with an assigned integer type. It's silently casted to an unsigned in that n, and then there's a subtraction of 2 unsigned values, capacity and signed, and that is compared with that n. And this is regular C++ with just interesting code with a font with ligatures for greater equal. So to silence if I would have written auto here, this would give us a compiler warning, oh, you're comparing a signed and an unsigned number. But the problem is not the comparison, the problem is that this subtraction actually creates still an unsigned number where the domain of subtraction of 2 natural numbers goes into the integers. And later on we have an additional cast, because actually that n there is considered a signed number because it's used in all different places where the signed type is required. It's only to silence this comparison that is defined as a size type, and it's cast back again. Casts are an indication of a problem in your type application. And at least we could have done a single cast instead of 2. So 1 place where you bend the compiler instead of 3 places there. Now what can we do about that? Well, we learned about code that is old enough to vote. Here we got design patterns that are old enough to drink legally in most countries of the world. There's a pattern called the whole value pattern. The whole value pattern is what we know about strong typing and so on. And where does it come from? Or what's the example? I go with that. We had another example by Arno Lepsic yesterday on how to do that. I did that already. That's a whole value pattern. It's from the checks pattern language of Ward Cunningham. Ward Cunningham is the inventor of the WikiWeb. Not Wikipedia, the WikiWeb, the original one, by the way. And I that's one of the slides I want to read out. When parameterizing or otherwise quantifying a business domain model, there remains an overwhelming desire to express these parameters in the most fundamental units of computation. Not only is this no longer necessary, remember this was 1995-ish, it was standard practice in languages with weak or no abstraction, my edition like C. It actually interferes with smooth and proper communication between parts of your program and with its users. Because bits, strings, numbers can be used to represent almost anything, any one in isolation means almost nothing. Therefore, construct specialized values to quantify your domain model and use these values as arguments of their messages, which is functions in C++ terminology, and as the units of input and output. That's what value types are for, strong types. Make sure these objects capture the whole quantity with all its implications beyond merely magnitude, but keep them independent of any particular domain. So we add functions and operators to operate on them. Include format converters in your user interface that can only correctly and reliably construct these objects on input and print them on output. Constructors, I/O operations. Do not expect your domain model to handle string or numeric representations of the same information. So no mixing up of ints and the strong thing. No implicit conversions. Always be explicit when you interpret a value in a different domain. Think about that. Take it home. This is the most important slide for you to take home if you haven't heard about that. Now, if I do my strong types and read everything in nice value type classes, should I make these value types default constructible by defaulting the default constructor, for example, or not defining a constructor at all? And my take is yes, if you have a natural default or neutral value in your types domain. For integers, 0 is somehow the natural default value, which is okay-ish. But it depends on what is a major operation. If you use numbers for multiplication only, 0 might not be a very good default because then everything multiplies as 0 if you put that default value into the operation. So be aware of that. Sometimes you want the default value when it's very hard to figure out what the initial value should be. But there are tricks like using ternary operators or lambdas in place if you have complex logic to define what the initial value should be that give you a good initialization strategy without having the thing, oh, I define a variable and then I initialize this by assignment in a complex logic way, which is easy to get wrong or keep the value uninitialized. Don't define a default constructor or provide one or get one automatically when you have a domain where there is no natural default value. Example, poker cards, playing cards. What is a default playing card? All are equal, but different. There's no default constructor. Some people said, oh, okay, we can have a joker there. Yes, but how many jokers do you have in your deck? None or 3 or maybe 4 or an extra one, but that's not the default value. It's just an arbitrary special value in that domain. And you shouldn't have a default constructor when you have an invariant in your class that requires reasonable initialization. Someone would ask, yeah, what kind of types are there? Consider a cryptographic key. You don't want to have a default constructed cryptographic key because that's the first one everybody uses and everybody uses the same key. And that's the curse of many of the problems with security holes, using bad keys. And a cryptographic key, you don't want to have a default. I explained that already. And the reason for the problem is we have a relative value, the distance between two indices or pointers, and then we subtract 2 pointers and compare to the relative type again, and just to silence that warning in comparison, actually the difference between two absolute values should be a relative value. And standard chrono is the best example. There we have a duration, which is a relative value, and the time points, which are absolute. And if we subtract 2 time points, we get a duration. We add a duration to a time point, we get a new time point. And adding 2 time points is nonsense. It doesn't compile, which is good. If you model your domain values like that, make sure that you know if it's an absolute or a relative value. And just using an int doesn't help you a lot. Some people do a lot of 3D graphics or have a VEC 3D or VEC 4D, and it's very nice to work with them. But very often in the domain where they model and use them, they don't distinguish between location or position, absolute, and the displacement, which is also a vector. And that's representation is identical, but the meaning is different. And it might not make sense to add 2 absolute points, but it might make sense to subtract them to get the displacement between them. If you model generic unit frameworks, it's very hard to make that distinction correctly, especially when you do dimensional analysis. You end up with the same dimension, but with different meanings. So that's a hard part to solve in any generic units framework. But you don't have to do generic Unix frameworks. Just wrap your types accordingly your domain. So the mistake of Stepanov was to have size type and difference type not being a struct that have a distinct meaning from unsigned long and int, for example. There are more generic strong types. Björn Fahler, Jonathan Bocara yesterday, I forgot the name, I put it on the other slide. Jonathan Müller and me, I'm trying as well. I try to make it simpler than the other things like no constructors, just aggregates, and mixing in operators with empty base class optimization, so my types stay small as the original base types. And let's see how that works. I don't know yet if it works in general, but I think it's a nice idea to play with. Now, empty classes. I said, okay, they might be in the same quadrant as value types. There are things like you don't get something for nothing, or you get something for nothing, Calvin Henney. And in C++, empty classes, you can actually get something from nothing, for nothing. So they're considering safety, usually empty types can't go wrong because there's no data, nothing to lose, and that typically works. And you use them very often in combination, let's, for example, to create better value types by mixing in curiously recurring template parameter pattern or idiom into value types or other types. You get that mix in, you get empty base class optimization, so your types don't grow arbitrarily. Sometimes they are even used for empty base class optimization to make types smaller and more efficient. We have a whole set of empty types that give us information about other things like types and compile time values. We have tags and traits types, and that's all kind of making stuff work and figuring something out about the less safe parts to make their use safer. Examples are iterator tags that we use for tag dispatching to figure out what might be a better algorithm to call if we have a higher category iterator type. Or we have tags that allow us overload selection as well to give a better initialization behavior of some of the constructors. And there's a question. Can you walk to the microphone because then it's taped?
Oh, it's just a very short one. Do you consider types that are polymorphic and have no data members to be empty types or not?
The question is, are polymorphic types without data members empty or not? That they are not empty because they have a vtable pointer. And that's, you don't get a lot of let's say you lose a lot of the things that you get from empty types, because polymorphic types are not really empty. We can represent values as types, which is often used in metaprogramming, like integral constant ratio, to actually mark other types with the ratio, which makes them dimensional analysis easier. We have sequences to actually unpack tuples, which is a nice feature, but tuples are often overused. They only have use in generic code. We actually need them, but not in user-level code. If you have an abstraction, name it like that, don't use tuple. For substitution, failure is not an error application. Enable if is also an empty type that gives us interesting features. How does empty base class optimization work? In C++, the standard tells us that every type, regardless, occupies at least 1 byte. And today we can say 1 byte because we have standard byte now in the standard. But it doesn't have to, because if you don't have any bits to represent something, the compiler is allowed to leave out these bits if it can. And that's very often used as a trick to make things smaller. For example, unique pointer with a deleter object that is a class actually tries hard to make unique pointer only the size of a regular pointer, which is a nice thing to have because you don't pay any overhead in space if you use a unique pointer correctly. It's also good for CRTP mixing classes because they typically come only with other functionality that is and no data, and if they don't occupy extra space in your object, that's fine. There are some tricks to play out to have it work nicely with the empty base class optimization, that it actually works, and there are quite complicated rules to do so. And the thing is, if you combine something that has a data member with something that doesn't as base classes of a third class, then the third class only is as big as the one with the data member, like in this code example there. In C++20, the standard people, or some people actually figured out maybe we should make it a little bit simpler to apply that, and we have now an attribute no unique address that you can use for members that might be empty types and get rid of the complicated, convoluted infrastructure of inheriting arbitrary base types to have these, to make use of the empty base optimization. When does it not work? Well, if your class has a first member that is the same type as the base class type that is empty, you have distinct objects, the base object and the member object, and they have to have distinct addresses, and therefore they cannot be empty. They must occupy space. So there's a nice example here where we see that this EBO actually inherits from empty and has an empty member, and both would actually happen to be at the same address at the start of the object, and that will hinder you. Distinct objects have to have distinct addresses, distinct objects of the same type. Even though they are empty, these two will occupy space, and with some alignment we might even add extra space in the middle of the object. That is the glimpse of what I'm trying to do with my simple strong types. It uses aggregates, public members, not a big deal, it's just public. Structured bindings to work with the mix-ins to actually work with other types that just are aggregates to access the elements. So the operators work generically, they are all friends, so they in the struct, so they don't pollute the global namespace, but still work with the types that I use. There's an interesting variadic template to inherit from all the friends passing in the the derived class as a CRTP parameter, and it's applied here. We have our weight counter from the slides before that I didn't explain well enough. It's an unsigned type that is strongly typed, so it gets its own name as a tag, and it has operations on that type, equality comparison, increments, and output, and now we can use our counter perfectly in our test case without mixing counters, weight counters with other counters or other integers or unsigned numbers. There's another category of empty things that is halfway to the unsafe and maybe insane category. It's empty adapters. C++11 inheriting constructors made it, and variadic templates made it very easy to write adapters to standard containers. Like, oh, I have a set, I want to have that index operator for whatever reason, maybe because I want to write for loops like hell. And then you can actually provide these at a cost because they are not that cheaply implementable with standard set, but you might just like them. So you can actually write an adapter, indexable set, without any data in there, adding additional operations and maybe changing existing operations. And if you only exclusively use that indexable set in your system, you're fine. You better not upcast it to the set because then you lose all the facilities. And also it's very hard to downcast. Downcasting only works with, again, wrapping it within an indexable set and not via reference. Note, we don't have any virtual there. So if you overload a base class member function, it's not automatically called if you refer it through a base class reference, which is a good thing in that case. Next topic, empties are over. Pointers. We have a whole set of things that point somewhere. Jonathan Müller actually gave a talk at ACCU on I just want to point to something. And it's really interesting what's happening there. And we have types that are pointers in disguise, which might not be obvious that they're pointer. Even the standard library provides you with those types. And using anything that refers to something else requires high discipline. You should have your drill instructor in the background to watch what you're doing, because you don't want to shoot yourself when you use things that point somewhere. On the other hand, you need pointing things. For example, the managing types, they usually need pointing types to give out so they can keep track of the things that they manage. The OO polymorphic type, the polymorphism only works through pointers, or things that act like pointers, references, which is a better means. Some pointing types are even nullable. Dereferencing a null pointer is undefined behavior, boom. And a bad thing is all pointing types, regardless, can be made dangling. And accessing a dangling resource, accessing an object that's no longer existent, gives you very, very bad things. And you better not do that, because you're in undefined behavior land. There are sane uses of pointing types. You can make them smart, so they manage what they point to, like unique pointer. And the only place where it's very safe to use them is down the call chain. If you call a function taking something by reference, that's safe. Nothing bad can happen because you only can call it with an object existing. But if you memorize that reference somewhere else, either capturing it a lambda and do something strange with lambda, you easily end up in a situation where that reference is dangling. And then you're down here, or even way off the screen, lower left. So, In C++, one of the strengths, we can define things that refer to other objects, but the lifetime dependency is there. Often we have types that are these pointing types, that are class types, that are regular, that can be copied and everything, but they are not value types because they don't exist out of time and space. They don't exist on their own. If I have the number 42, it's always 42, regardless where it is. But if I have a pointer to a memory location where 42 might have been stored, and if that memory location is freed, my pointer is no longer valid, so it doesn't stay. Even the pointer value is the same. And pointers in disguise are iterators, smarter pointers, reference wrappers, references, views, and spans. The string view is a pointer. You might not see it like that. It's a pointer. A C array is a pointer, especially if it's passed as a function type, a function parameter type, because then it degenerates to a pointer directly. So the problem is dangling invalid reference pointers, null pointers, invalidated iterators because the container has changed, or past the end iterators, which are valid but which only support a partial comparison with other iterators. Iterators must be regular. That's a concept by Stepanov. Sometimes they don't need to be default constructible. I think that might have changed in between. And most iterators refer to other objects in containers, so they depend on the lifetime of another object. They are not values. They depend on the lifetime of another object, and changing that other object might actually break the iterator. And there are special values you have to deal with. You consciously have to make sure that you know that this iterator has a special value. And sometimes the only means to figure that out, have the original container at hand to figure out if that iterator actually is invalid. For example, in C++, if we have a single iterator value, we have no idea to know if that iterator value is valid or not. High discipline. You need to have things together in context. Ranges might make things a little bit saner in that sense, but I haven't tried enough of ranges to understand if there are dark holes as well. Reference wrapper. Who's using reference wrapper in their code base? Who knows that reference wrapper exists? Who has never heard of reference wrapper? Now you have. It's used in the standard library. It was invented for bind. It has some nice properties. Some people say it has ugly properties, but it's sometimes useful in generic code to pass it around. To pass and to keep classes that hold a reference that cannot be null and still make them regular by making them assignable. Because you cannot reset a reference member, but you can reset a reference wrapper member. Smart pointers. There is a standard library fundamentals technical specification where we have the observer pointer in there. This is a pointer that I would like to get for referring to single objects or nothing. One could say, okay, if we don't need that nothing, why don't we use optional to reference to the type? Well, unfortunately, optional references are not allowed. Maybe yet. So it's either optional reference or observer pointer, but not defined like that because I want more semantics. But maybe it's the right way to do. I'm not sure. Shared pointer, if you ever have seen one of Nico Yosuti's talk on shared pointer, if you haven't, look it, has its own issues. It can be a nice thing, especially if you come from Java, but you end up with more problems than you might have experience in Java with shared pointer. Better use unique pointer exclusively and know when you refer to something that's held by a unique pointer and manage the lifetime explicitly, because that's much easier to get right and fewer surprises. String view is another pointing type. It's okay as a parameter type for functions, because passing pointing things down the call chain is safe. But never return string views from functions, especially if the caller doesn't know about the lifetime of the underlying object that it refers to. Return strings. It's good for replacing character pointers and string constref parameters by string view. It can be better performance if you're passing string literals. But be aware, if you have generic code, it's very hard to get right. I tried to write a paper on replacing all standard library overloads that have character pointers and string references, const string reference, by string view, and I failed horribly. Put in a lot of work without getting anywhere. It was unimplementable and would break existing code. C-style pointers, I don't want to go into detail, don't use them. They are dangerous and insane. They allow arithmetic, they allow indexing, you never know what you're doing. You have things like where is const belonging on the right, on the east side. And it's very hard to use them safely and sanely, and they require high discipline. So if you meet a C programmer, he or she or they need to have their drill instructor in their back of the mind every single piece of code that they write. Because they use plain pointers, they use dangerous things, and they will shoot their food without recognizing. And if you program the same way in C++, that's a way to get into insanity land. And undefined behavior, unicorn land, or whatever you call it. Don't do it. All pointing types, and sometimes we are not even aware that they are, live in the dangerous quadrant requiring high discipline. The bad thing is, very often code just compiles. Like the integer promotion rules nobody can remember, who knows all the iterator invalidation rules in the standard library containers? When I insert something in a vector, are the iterators valid? It depends. When the vector needs to reallocate, all iterators are invalidated. When I insert in a list, are the existing iterators still valid? Yes. Should we use list? No. There are ideas on static analysis to figure out if pointing types are only used in a sane way. We are trying to implement that for our IDE. Not sure if that works out. We have languages like Rust who try to give you that safety guarantee, but the only interesting things that you can write in Rust that are interesting require you to use unsafe. At least you're honest in that way. So we get there. Temporaries. Another thing that's bad. Java programmers don't know that because there you have garbage collection, everything is a reference. In C++ you get interesting undefined behavior. Oh, yeah, one idea I had, maybe we should make sure that we never return an iterator from a temporary container. Because when that iterator is used, the container might be gone. One idea would have these referenced begin versions and delete the refref version, but I'm not sure if that's valid, and it would require the const refref deleted as well. An idea. Think about it. If you believe that's a good idea, tell me if you believe it's a bad idea, explain me why. And I'm sure it will never be standardized because it might break existing code that's wrong anyway. That's always the danger. Managing stuff. Richard Gordon told me when trying to figuring out a name for that, oh, I call these monomorphic object types. They have state, they have behavior that's interesting, they keep changing their state, so they are not values. But they don't inherit from something interesting and don't provide virtual member functions. I came up, well, these types actually manage stuff. You have a lot of managing types in the standard library, those that do RAII, those that manage memory, all kind of resource management. I talked about that yesterday a little bit. And they might need pointing types to actually make use of that, and that requires discipline to only call that down the call chain. Very often managing types are allocated high up the call chain on the stack and then passed by reference down the call chain so that they remain the same object and you can refer to it. Things like the manager design pattern, and I'm running out of time, I don't want to go into that detail. RAI was the talk about, I talked about yesterday intensively. Dynamic polymorphism. Sean Parent has the opinion inheritance is the base class of evil. And I started out in C++ and I liked inheritance because that was cool and new and fresh in around 1990. And today I hate inheritance, at least dynamic polymorphism, because it makes your design and life interesting. That table is something you should memorize, or at least know that it exists and know where to find it, produced by Howard Hinnon, showing you what you get when you define one of these special member functions or nothing. And there are a few holes for backward compatibility. The red ones, if you define a destructor, your objects are still copyable. And you get a defaulted copy mechanism for that. You don't want that, because if you define a destructor with semantics, you want something interesting happening, and usually your types are no longer value types. And you definitely don't want a defaulted copy constructor. The good thing is, when you declare a move assignment, all the other interesting things are deleted or not declared, so nothing bad happens. That made me to come up with a suggestion: whenever you define a destructor, like you are in a base class of a dynamic polymorphic hierarchy, you better use a declare move assignment as deleted, and then nothing bad happens. You have your user declared destructor, and you might have additional constructors and a default constructor, but you never are able to unintentionally copy and thus slice your hierarchy objects. Good. That's how OO hierarchies should be done. Very often they are applied badly. That's a typical textbook example on object orientation. We have a person class, and student and professor inherit from person. Is that good design? Who has written class hierarchies like that? Confess. It's a bad idea. Don't. There are a few situations where you actually have dynamic polymorphic behavior, where you change behavior at runtime in a polymorphic way of a common abstraction, and you can program to the base class. In C++, we have a much richer vocabulary on programming against abstraction, like against the template parameter, and make it statically polymorphic at compile time, which is first more efficient and safer. And you don't need to use these reference things that can be dangling. So, what are sane combinations of special member functions? The first thing is, two things are the green ones, aggregates and value types. Aggregates by definition are value types, unless you have an interesting member in the aggregate. Everything is defaulted, and maybe in the default constructor you have none because you have a class invariant, but that's good. You have manager classes that are not copyable, often not movable. Sometimes you might want to move them, but then you spell it out. You have usually an expert level code in the destructor to clean up stuff, like vector has to delete all the elements in its destructor. That's expert level code. You don't want to write that every day because it's too easy to get it wrong or even get into undefined behavior land, which vector might be if you do it yourself. RAI classes have user declared and often user-defined destructors and better not be copyable but might be movable if you need that. OO base classes should have a defaulted virtual destructor in the base class only, it's automatically inherited, and not be copyable or movable. You might retrofit value semantics to a manager class like it's done for vector, but that's really expert level territory. It requires a high expertise to make it work correctly. Don't do that every day. Do that if you're a standard library implementer or I would say a standard library level library implementer, but not in day-to-day code for your domain because it's too easy to mess it up. You can actually combine OO dynamic polymorphism with valued semantics. Sean Parent showed that. He has a nice talk. I believe it was also on CppCon or some other venue on video. I don't want to go into the details because it's, once you got it, it's easy to understand, but to understand it is really hard. So if you look at our landscape of safety and sanity, there are many things to look out for. A lot of things can be done, put into the safe quadrant up here by library experts, by using good things. I didn't go into standard variant for variation at runtime, but that are the things you can do. And remember, the built-in types are close to insanity. Just remember that the next time you spell out INT. Takeaways. Learn to appreciate the C++ type system. Every cast is an indication to think and refactor. You could even treat every cast as a mistake of your program design. Model with value types almost always. Be aware when you model with dimensions about the distinction of relative and absolute values in the same unit. Wrap primitive types using the whole value design pattern. And even a named simple struct wrapping an int is better than using int. Be aware of the required expertise and discipline for manager types and OO hierarchies. It's not that simple. It's easy to get wrong or get into undefined behavior land, especially when you combine them. Be disciplined about pointing types, and this includes reference and string view. It's not impossible to get it right, but get your drill instructor in your back of the head every time you use a pointer or reference. Every time you use something that's not a value. Run away from weird special member function combinations, even if they are defaulted. That's danger lurking, might explode in your face. Usually they try to do too much or the wrong thing. And that's it. Questions? For you to read. I think we can take 2 or 3, maybe 1.
I have a question about pointing types. So you said it's dangerous, but if we talk about unique and short and shared pointers, it feels like they kind of completely different part of the quadrant. They are much safer, and actually it requires much less discipline to everything else.
The thing was, unique pointer and shared pointer require less discipline than other pointers. Yes, but they still require discipline, like not calling get arbitrarily and converting them to the plain pointer. And also they might be null, which is also something we have to take care of. So better unique pointer and shared pointer than plain pointers, but better use just values if possible.
Thank you.
That's my guidance.
When you were talking about ranges and deleting the begin and end for R values, one thing that I think is interesting about range v3 is that the views that you get, which are similar to spans, which are kind of can dangle if you're not careful, you can only create a range out of an L value of a container. You can't create one out of an R value just precisely for that same reason of you wanting to not be able to get iterators. So it kind of follows along the right pattern.
Thank you for that information. I haven't learned that yet.
Okay. Also, a question.
And do you want a hat? I have 2 left, so the most interesting question. Get it.
Question about the ranges and follow up on your remark about when you use the returning iterator from the container that's local and maybe already deleted out the scope. So you need for regular types a lot of time to have an identity element for the ranges, on your iterator, and you usually use it at some end or something as a special value to indicate on that structure. So I mean, what do you think? Like, what's your opinion on using that as a zero identity element? And why wouldn't you just return that as a special element?
I'm not sure if I understood your question. I said, be aware of iterators. They might be bad, but you have to use them anyway. Is that your statement?
Yeah, well, you have to use it, and sometimes it's a very best that you can find is you just have a range and you have this one special iterator that will be our identity element.
Let's say that design decision was taken when Stepanov wanted to make the STL compatible with C arrays. And we cannot change that at the moment, but ranges might help with that because you no longer have these pairs that might not work together. And again, you must use iterators, but better just pass them down the algorithm library or make sure you're disciplined with them. It's not, you cannot use them, it's just be disciplined with them. And sorry, I cannot answer that better in the moment. I think we need to finish up. Is there one final question, or is that?
Should be quick. I love your part about being very careful with built-in types. Unfortunately, particularly people with C backgrounds, Fortran backgrounds in scientific computing, they don't feel like they're getting the most out of the compiler unless they're using the bare types. How do we instill a trust for the compiler in them? Do we teach maybe benchmarking exercises? How would you go about doing that, especially at a university or in a company?
I would say got bold.
Oh, that's great. Thanks.
Okay, thank you very much. Have fun. I have 2 hats left and a lot of Swiss chocolate. Come see me and grab stuff, grab the chocolate. And there's a lightning talk tonight, so maybe I give them out there then.